I want to take a minute to just quickly review a little bit of the stuff we were talking about last semester. We were talking about force and its relationship with rotation, which we actually know is torque. Okay, and so we had these angular things and these linear things. Linear is what we spent most of our time doing. Forces cause acceleration. That's a linear concept. Torques cause an angular acceleration. Okay, so torques, this is a force's ability to cause rotation. So these cause rotation. Now you guys have a couple equations that relate torque and force. First we have torque. The torque acting on an object is given by the force acting times the lever arm over which it acts, R. So when you have like a door, if this is a top-down view of a door, okay, so the hinges are over here on one side, you come over here and you push right here to open the door. You don't push right here because then you have to push with extra force, right? The lever arm, the longer the lever arm is, the greater its ability to cause rotation. So you push right here, and not only do you push right there, you push perpendicular to the surface of the door. You don't push at an angle like this. You're not trying to get the door to slide sideways. You're trying to get the door to rotate around like this, right? And so torque equals force times lever arm, and this equation is valid when the force is perpendicular to the lever arm, okay? And for most of what we're going to do, that's good enough. So if this door was, like, if we wanted to calculate the torque on a door, if this door was 1 meter wide and the force that you applied was 15 newtons, then you'd say, okay, force times lever arm equals torque, so 1 times 15 equals 15, and now your unit is Newton meters. Okay, so torque is force times lever arm. It's a force's ability to cause rotation. That's one thing we learned. We also learned Newton's second law for torque. Okay, remember Newton's second law says that the net force acting on an object is equal to mass times acceleration. Okay, well, there's an angular equivalent to that, which says the net torque acting on an object is equal to its moment of inertia times its angular acceleration, I alpha. Now, moment of inertia is an interesting concept, but essentially it's the sum of all the masses around the axis of rotation. So for most things, there's 2 or 3 main equations we use. If all the mass can be considered to be along the outside edge of something, so like a thin wheel where you've got just a few spokes coming in, but most of the mass is along the outside, then I equals mr squared. Okay. If it's a solid disk, so this is all shaded in because it's a nice uniform solid disk, mass is distributed everywhere, then it's 1/2 mr squared. Okay. And then spheres and rods and other things, they have their own formulas, and those are in your book. You guys have seen those before. Okay, so what can we do with these? Well, let's take a look at, say, page 224 in your book, number 84. Okay. I want to just quick review how we solve one of these problems. It says a bicycle wheel with a radius of 38 centimeters. So R equals 0.38 meters is given an angular acceleration, that's alpha, of 2.67 radians per second squared. 2.67 radians per second. Okay? And that's applied by a force, F, equals 0.35 newtons, and this force is applied on the edge of the wheel. What is the wheel's moment of inertia? Alright, so here's what we have. Always like to start with the picture. Wow, that's an awesome circle. Okay, so this wheel has a radius of 0.38 meters, 0.38, and a force is applied causing it to rotate. This force is 0.35 newtons. Okay, and so we're supposed to find I, the moment of inertia of this wheel. I equals what? Okay, well, we're going to use both of these torque equations together in order to get there. Okay, so what we can say for sure, torque is equal to force times lever arm, F times R. Well, that means we're going to take this 0.35 newtons times 0.38 meters, because that's the lever arm, that's the radius of the wheel. And when we do that, Okay, we're going to get the torque that causes this thing to rotate, and it will be in Newton meters. So 0.35 times 0.38 is 0.133 Newton meters. Now that is not the answer to the question. The question said find I. Okay. Now the only equation I know that has I in it is T equals I alpha. Okay. And so since we were given alpha and I can find torque, now I can find my moment of inertia. So I'm going to say, okay, my torque, which is 0.133, equals I times its angular acceleration, which we were given, is 2.67. So then I'm going to divide both sides by 2.67, and I get 0.0498. So I equals 0.0498. Now the units of moment of inertia is kind of interesting. Torque is measured in Newton meters, okay? And you just divided torque by angular acceleration, which is radians per second squared. A Newton meter divided by a radian per second, okay? Golly, that's going to be kind of a complicated, confusing unit. But if you come up here, it's also just mr squared, which is kilogram meters squared. So how did that get to be that way? Whoops. Well, if you look, a Newton is a kilogram meter per second. Kilogram meter per second squared. Okay. Then a Newton meter, so now this is kilogram meter squared per second squared, and then you just divided off those per second squared, so that's gone. Now remember, the radian is a dimensionless unit. It's just a placeholder, right? Because it's a meter divided by a meter. Okay, so the unit is a kilogram meter squared for the moment of inertia. Okay, so that's Newton's second law, and force or torque is force times lever arm, and that helps us get through a couple problems like this. Now they can get a little bit more complex than that, not too bad, but let's take a look at one more. We've got a pulley, and over here we've got a mass, and the mass of this thing is 3.8 kilograms. Okay. And hanging down on the other side there's another mass, and this one has a mass of 3.4 kilograms. Okay. The pulley is a uniform solid disk. Okay, so that means its moment of inertia can be given by mr squared. Okay. It has a radius of 3 centimeters, so this distance is 0.03 meters, and it has a mass of 0.8 kilograms. Okay. We're going to do this for two cases. Okay. We're going to do A, the frictionless case, and B, with friction. Okay. So A says if this is frictionless, what is going to be the angular acceleration of the pulley or the linear acceleration of the masses? Okay. Now, you have to be very, very careful when you do this, because in the past we've considered all pulleys to be frictionless and massless, but now we know they are not, right? They actually have a mass, and they do resist rotational acceleration. Okay, that's what the moment of inertia is. It's the equivalent of mass. Okay, so this 3.8 kilograms is trying to pull this way. Well, gravity is trying to pull it this way, and the tension in the string over here, okay, I'm going to call this T1, is pulling up. Okay, over here we've got gravity pulling down, and we've got T2 pulling up. Now, the question we have to ask ourselves is, which way is this thing going to go? Well, this mass is heavier, so this down force here is greater than this down force here, so the whole thing is going to accelerate like this. Now, I'm going to give that the positive direction. That means anything moving in this counterclockwise direction is positive. Okay? And that's going to be important. It's always important to get your frame of reference and your directions established. Okay? Alright, T1, since a string carries that, this is also T1. Okay? T2, this is also T2. Now, what you have to remember is T1 is not the same as T2. If they were the same, then the net torque acting on this pulley would be 0, and the pulley wouldn't accelerate. And if the pulley doesn't accelerate, then the strings can't accelerate, and if the string doesn't accelerate, then the blocks don't move. Okay, so the torques is not 0, so these forces cannot be 0. Alright, so what do? Well, this is one of those cases where it's best just to look at every piece individually. So we've got this piece, I'm going to give it 1. We've got this piece, I'm going to label this piece 2. And we've got a third piece, okay, the pulley up here. This is number 3. Okay, so we're going to look at each one of these pieces individually and see if we can figure anything out. So let's start looking at pulley number 1, or object number 1, right? Object number 1 is the big, heavier mass. Okay, and so let's see, the positive direction over here is down. So let's go ahead and see what we've got. We've got the net force is given by 3.8 times 9.8 minus T1, and that equals 3.8 times A, right? That's Newton's second law, which is net force equals mass times acceleration. So here's one force, here's our other force, here's the mass, here's the acceleration. Okay, and we can do a little bit of simplifying on that, but not a whole heck of a lot. We don't know T1, we don't know A. All I can do is multiply the 3.8 and the 9.8. And if I do that, we see 37.24. So I can say the net force over here is 37.24 minus T1 equals 3.8 A. Okay, that's all I've got for number 1. So I have T1, which is an unknown, and I have A, which is an unknown. So I have 2 unknowns, so I definitely need another equation. Okay, so let's come up to number 2, this other block. Okay, if we look at that one, again we're going to do the same thing. Net force equals, and remember on this one positive is up because we're on the other side of the pulley. So we've got T2 minus 3.4 times 9.8 equals M 3.4 times A. Okay, so this is again Newton's second law. Net force equals mass times acceleration. There's our mass, there's our acceleration, and here's the net force. Okay, again, not a lot of simplifying we can do. All we can do is multiply those numbers together. 3.4 times 9.8 is 33.32. So I have this is equal to T2 minus 33.32 equals 3.4 A. Now, I have another unknown. T2 is an unknown and A is an unknown. So if we add that all up, now I have 3 unknowns. I've got T1 as an unknown, I've got T2 as an unknown, and I've got A as an unknown. Now these accelerations in both these equations are the same because they are connected by a string. Okay, so the last thing to do is we need an equation for every single unknown, so I need a third equation, so I've got to go to my third object. Okay, and I'm going to do the same thing on this, although this one is a pulley. Okay, so instead of looking at net force, right, because it's not trying to be moved up or down, it's trying to be rotated, I'm going to look at net torque. Okay, and net torque is the sum of the torques. Now, there are 2 torques. T2 is causing the torque, and T1 is causing the torque. T1 is causing the positive torque, so I'm going to start with it. T1 times the radius. The radius is 0.03, we know that. 0.03 minus T2 times the radius, right? That's force times lever arm, equals I, which we can find, mr squared, but I'm just going to write I for now, times, so I have 0.03 T1 minus 0.03 T2 equals I. I we know is mr squared, so m is 0.8, r is 0.03 squared alpha. Okay, now it looks like I just threw in another unknown because I had an A here, and now I have an alpha here. But there is a relationship between alpha and A. Alpha times the radius is equal to A. Okay? Which means I can replace alpha with A over r, right? If I divide both sides by r, then I can see that alpha is equal to the linear acceleration divided by r. So 0.03 T1 minus 0.03 T2 equals, okay, let's go ahead and find our moment of inertia, 0.8 times 0.03 squared is 0.00072, 0.00072, and then we're going to go ahead and put in A over R. A divided by 0.03. Okay, and we can simplify this one more time. 0.03 T1 minus 0.03 T2 equals, let's see, 0.00072 divided by 0.03 equals 0.024. Equals 0.024 A. Alright, so now it's just a matter of solving for one of these T1s or the other and plugging it into another equation and then doing that one more time. Okay, so let's go all the way up to step 2, right? I now have 3 equations and 3 unknowns. Let me highlight that for you. Okay, here's an equation. Okay, 0.03 T1 minus 0.03 T2 equals 0.024A. It's got 1, 2, 3 unknowns. Here's another equation. T2 minus 33.32 equals 3.4A. It's got 1, 2 unknowns. Okay. Here's another equation. 37.24 minus T1 equals 3.8A. It's also got 2 unknowns, but these 2 unknowns are not the same. Okay. So what I'm going to do is I'm going to go ahead and I'm going to solve one of these equations for T1 and plug it into another one that also has T1 in it. So if I look at this equation right here, 0.03 T1 minus 0.03 T2, so I'm going to go ahead and I'm going to divide everything by 0.03 just so I can get rid of that. And if I do that, I get T1 minus T2 equals 0.024 divided by 0.03, which is 0.8, equals 0.8A. Okay, so now I have T1 equals 0.8A plus T2. Okay, now I can take this one and I can sub it all the way back up into the first one. Okay, and that first equation, if we take a look at it, says 37.24 minus, now I need T1, which is 0.8A plus T2 equals 3.8A. Okay? Alright, so now I'm going to distribute that negative, 37.24 minus 0.8A minus T2 equals 3.8A. Okay? Add over my 0.8A and also my 37.24, so 37, well, we'll get there, 37.24 minus T2 equals 4.6 times A. Now I've got 2 options. I can solve this for A or I can solve it for T2, but either way it's going to end up being subbed into equation number 2. So T2 looks like the easier way to go, so we'll say 37.24 minus 4.6A equals T2. Okay, so now I've been able to eliminate one of my unknowns. I was able to eliminate T1. Now I'm going to put this back up in here and see if we can eliminate T2, and if we can, we're done. Okay? So I have this big long equation, 37.24 minus 4.6A, that's T2, minus 33.32 equals 3.4A, right? I've just subbed that into my second equation. So now I've got to collect all my like terms. So I've got to add that 4.6 over and I've got to subtract these 2 things. So 37.24 minus 33.32 is 3.92 equals, and said 4.6 plus 3.4 is 8A. Right? So 3.92 divided by 8 is 0.49, and so the acceleration A is 0.49 meters per second per second. Okay, that is a big, long, complex, complicated process, but you're just looking at all the forces and what motions they cause on each one of those things. Okay, so I'm going to have you guys do a worksheet today that's got a couple of these problems, or I want you to work them. You got to think your way through. Shouldn't be too bad, but it will take a while because it is this big long process like this.